Welcome back, Level 2 physicists, continuing on with the electromagnetism external, looking at electromagnetic force today. Okay, so remember our right-hand rules. Okay, so the first one is that the thumb points in the direction of the current, fingers point in the direction of the field lines. This is known as the right-hand grip rule. And the other right-hand grip rule is that fingers point in the direction of the current, okay, traveling around the wire, and the thumb points towards the north pole of the magnet. And then we have the third right-hand rule. And in this case, with the right hand here, okay, so the thumb points now in the direction of the current, the fingers point in the direction of the field lines, and now the palm points in the direction of the force that the wire, which is carrying that current, will experience. Okay? And how do you represent the direction of a that's perpendicular to the paper? Well, into the paper will be a cross, and out of the paper will be a dot, okay, in 3 dimensions. So looking at this example here, a current carrying wire is placed in the magnetic field, and the magnetic field exerts a force on the wire. What direction is that force? Okay, so the one on the left, okay, so the current going that way, it's going from north to south, which is your fingers, so it will be pushing up, whereas in the other case, now the current's going the other direction with our right hand, north to south again, the direction of the magnetic field with our fingers, and that means the force is going to be going down, so the wire will go down. Okay, so the right-hand rule can also be used with electric generators and motors, because when the electric field or electron current is passed through a magnetic field, you get motion, because you get force, electromagnetic force, going down on the right-hand side of the loop, and electromagnetic force going up using the right-hand slap rule on the left of the loop. So the loop basically rotates in the magnetic field. This is the basis of motors and generators. So for motors, they convert electrical energy into kinetic energy, kinetic energy, or the energy of motion, whereas electrical generators convert the energy of motion into electrical energy. And these are examples here, the top one being an electrical motor, and the bottom one being an electrical generator. So as you move it, it changes the position of the current, so it exerts a force which keeps it going and generates a current in the wire. So in terms of fields, okay, so we've looked at gravitational fields in mechanics, okay, so that will be equal to force over the mass, or newtons per kilogram. Electrical fields, which you looked at the start of this external, is force over Q, the charge, so it'll be newtons over coulombs. And then we have magnetic field, which is the force over a current. Okay, so newtons per amp, which is given the units of Tesla, so I think Elon Musk. And this is down to the concept of magnetic flux. So the magnetic field strength, B, is sometimes referred to as the magnetic flux, okay, and it depends on how perpendicular the current is in this wire that's experiencing the force is in relation to the field direction. Okay, so if the current is at right angles to the magnetic field going from north to south, you'll get maximum flux, okay, maximum force. If it's kind of at 45 degrees, you'll get less flux, and if it's parallel, no flux is given. It's 0. Okay, this is the basis of course, magnetic field strength. So if you have a wire going through a magnetic field, the force of wire on the wire, the electromagnetic force of the magnetic field, is proportional to the charge moving perpendicular to that field, so at right angles. Because of these, the perpendicular component must be used in the calculation. So the magnetic field strength B will equal the force divided by the current times the length of the wire in the magnetic field times sine theta. Okay, because remember, if sine theta is 90, so if theta is 90, then it'll equal 1, so it'll be the maximum. Or if sine theta is 0, it's parallel, it will be 0. So there'll be no experience of force. Okay, so B equals F divided by IL sine theta, which can be rearranged to force equals Bill sine theta. Okay, so force is a magnetic force in newtons, magnetic field strength is B in Tesla, the current's in amperes A, the length of the conductor in the magnetic field is L, which is in meters, and the angle between the magnetic field and the current is in degrees. So in terms of forces on a charged particle, when there is a magnetic force on a current carrying wire, the force is really on the moving charges inside the conductor. That's what actually current is. Okay, so since single charged particles can experience a magnetic force, we're moving to a magnetic field. Using the equation force equals Bill sine theta, we also know that velocity equals the length divided by time. So therefore length of this proton moving in this case is going to be velocity times time, and current equals charge divided by time. So force will equal B times Q over T. We just substitute in for I, times length, which is VT, sine theta. The T's cancel out, so the new equation is force equals BQV sine theta. Okay, so you can see that with particles moving across fields. So remember, current moves from positive to negative. Okay, so in the top example, the positive, the current is moving to the right of the page. So using the right-hand slap rule, this time going away from you, so it's going to go down. The converse is for the case of an electron, so this time it's going to be the current moving in the opposite direction. Again, remember, going from positive to negative. Okay, so this means that the particle, the electron, is going to be moving up. Okay, and for the corresponding proton in a magnetic field into the screen, it'll be going up. And magnetic field into the screen for an electron, it'll be going down. Okay, the faster the electron or proton moves, the more extreme, the slower the particle moves, the more extreme that kind of movement. Okay, because the force is always perpendicular to the motion of the particle. So finally, looking at creating voltage in a wire, the equation is the voltage equals magnetic field, of course, in Tesla, times the velocity of the wire moving in that field in meters per second, times the length of the wire in that field, times sine the theta of the angle between the magnetic field and the wire. And that's the last equation that you need for this external.